Hello, I am Sina Yari. I will talk about our paper that you see the title here. In a nutshell, our paper is a study of the existing methods that consider power consumption and reliability jointly in the embedded systems. It is my honor that I have this lecture about our paper, and I appreciate all those who gave me this opportunity. More about me. I am a master's student at Sharif University of Technology. Also, I am a member of the Embedded System Research Laboratory at the Department of Computer Engineering at Sharif University of Technology. In my presentation, I will talk a little about the principles of embedded system. Then, a small overview of related work will be discussed, and we can see how the proposed methods can be different from each other in terms of assumptions and goals. As I said in this paper, we will discuss some existing methods. So after the related work, in the method discussion section, I will explain about the selected methods. After that, I show our experimental results, and the conclusion section will be the last part of my presentation. Embedded systems are the most widespread computers utilized in many industries, such as the automotive industry, medical devices, and smart city traffic controllers. These systems are designed to be a part of a big system, so this is the reason we call these systems embedded. As you can see the applications of these embedded systems in this picture, it needs to consider several requirements. For example, an embedded system should be reliable because this system is designed to be used in a critical environment, and it should tolerate faults, so reliability is an important parameter. Also, getting the right answer is not the only condition for the system to work correctly. This system must be able to produce this correct answer before the dedicated deadline. Another aspect of these systems is power and energy consumption. Most of the embedded systems are battery-based, so these systems should consume low power. But it is not easy to satisfy these requirements because there is a contradiction between the available methods for each of them. For example, power management techniques like DVFS and DPM reduce the reliability of system. On the other hand, fault-tolerant techniques increase power and energy consumption because they are redundancy-based. Therefore, there is always a challenge between power consumption and reliability in embedded system design. Let me talk about principles a little to address our assumptions. Two major system models are homogeneous and heterogeneous. Homogeneous systems are used for many years, and this system model includes several identical cores in a chip. But as you can see here, an abstract view of a heterogeneous system. These systems, as a new generation of system models, are used in the design of embedded systems to benefit from the low power and the high performance cores simultaneously. For example, the ARM Big Little is a heterogeneous system that consists of Cortex-A7 core as a low power core and Cortex-A15 core as a high performance core. Another assumption is about the task model. Tasks can be in graph-based or periodic. Each of these task models are common, and the system determines which task model to use. If there is a dependency between task execution, the task graph is used. But if the tasks require periodic execution, the periodic task model is used. For power consumption, as other works, we suppose the power consumption includes static and dynamic parts. Also, in general, fault-tolerant techniques can be divided into two categories: Active and passive. Active techniques use fault detection to increase system reliability. One of the most popular active redundancy techniques is standby sparing. In the standby sparing, execution is switched to the backup unit when a fault occurs in the primary unit. Hot standby sparing and cold standby sparing are prominent types of standby sparing. In the hot standby sparing, the primary and the backup units are both set up together, and if a fault occurs in the primary unit, the backup unit immediately begins to execute tasks. But in the cold standby sparing method, the backup unit is off until a fault happens in the primary unit, and after that, backup unit starts to execute the tasks. The switching speed between primary and backup units in the cold standby sparing method is longer than in hot standby sparing. Also, NMR and task replication are the most popular passive redundancy methods. NMR uses redundant hardware to tolerate faults, and task replication employs software replicas to satisfy the reliability target. Here you can see the different fault-tolerant techniques in the picture. In this table, a series of works are categorized according to the fault-tolerant technique, task replication, and standby sparing that you can see here. We can see that different task models and different architectures are used. For example, task graph, frame-based, and periodic task models are used, and for architecture model we can see both heterogeneous and homogeneous. Also, some constraints are defined in the system, such as power, energy, and real-time constraints. After that, the proposed method is presented to achieve the set goals, which you can see in the table. We selected two of the most popular methods to evaluate the energy and power consumption of fault-tolerant methods. Rohbani 2017 proposed a method that considers a standby sparing system and addresses the problem of core type selection in heterogeneous system and frequency value of primary and backup cores. Heterogeneous systems can have different power and energy outputs by executing the tasks on the different islands. On the other hand, choosing the proper frequency has a great impact on power and energy consumption and also in reliability. For this reason, the methods proposed using the standby sparing technique consider the type of core and frequency value. Rohbani 2017 has divided the type of primary core and frequency value selection into 6 categories. This study states that the cautious choice of the type of primary core and the overlap between tasks execution can help to reduce energy consumption. To this end, the methods used in the mentioned paper have been evaluated. These methods can answer the two basic questions. First, which type of cores should be selected as primary core, low power core or high performance core? Second, how to consider the frequency of primary core to reduce energy consumption. 6 possible approaches are here, and you can see faster static, slower static, faster minimize overlap, slower minimize overlap, faster overlap aware, and slower overlap aware. Here, faster means we select the high performance core as the primary core, and static means the frequency is a static value and it doesn't does not change. Minimize overlap scheme adjusts the frequency of the primary cores so that the primary and backup tasks are executed with the least possible overlap. For this purpose, the frequency of the primary core is selected such that the execution of primary tasks ends before the start of the backup tasks. And in the overlap aware method, unlike the minimize overlap scheme, it is possible to reduce energy consumption by overlapping the execution of primary and backup tasks. This overlap is obtained by solving an optimization problem. On the other hand, the proposed method in HAQ 2013 is a task replication method. In this paper, the energy consumption is minimized by considering a reliability target and the frequency scaling effect. Various heuristic schemes can be considered to select the tasks for mapping. As you can see here, we have choose a task that has the largest energy saving at first, or choose a task that has the largest power saving at first, or choose a task that has the largest utilization at first. For this purpose, the concept of the energy frequency reliability table is used to implement the mentioned heuristics. This table helps to find the proper number of replicas and frequencies to maintain reliability, and then this leads to the energy and power consumption to be reduced. Until now, we discussed briefly prominent standby sparing and task replication methods. Here, we will show our experimental results. For this purpose, we used Gen 5 and MacBat simulators. The Gen 5 simulator is responsible for defining the system model. As shown in the right table, we considered the ARM-based platform and used ARM Cortex-A7 and ARM Cortex-A15 as widely used cores in the embedded system to evaluate our proposed methods. So we suppose that our system has equipped with DVFS and DPM techniques. Then when it is needed, we can use these techniques to manage power and energy consumption. Also, MacBat simulator has also been used to obtain the information needed, such as power consumption and execution time, on the target system, as you can see in the left table. The task set is also selected from the MyBench benchmark, which is designed for embedded system applications. To evaluate the standby sparing methods, we implemented the static, minimize overlap, and overlap avail methods in fast primary and slow primary modes on heterogeneous system. We consider different utilizations, and it is well to mention that according to the optimization problems and frequency assignment scheme, the slow primary overlap aware and a slow primary minimize overlap are almost in the same behavior. As shown in the chart, methods that consider dynamic frequency for standby sparing techniques and perform overlap between primary and backup tasks can reduce energy consumption relative to the static selection method by an average of 13%. Also, as we can see here, the workload has a significant impact on deciding which method should be selected. For example, if utilization is equals to 0.2, it is better to use the overlap avail method instead of using minimize overlap to schedule the tasks that have some overlap between primary and backup execution. On the other hand, the chart shows when the utilization level increases, choosing the core type is more effective. Therefore, we can assert that when a standby sparing method is applied, we should consider workload, primary core type, and primary core frequency. According to our constraints and system specifications, to achieve a low power and energy system, we can add some overlaps between the execution of tasks and reach to our goals. The homogeneous system is considered to evaluate the task replication method. This is because we want to run equally the primary and replicas, and there is no need to synchronize tasks and replicas. We evaluated the impact of frequency and the minimum number of replicas on energy consumption by increasing utilization and by increasing the number of cores from 2 to 8 under a given reliability target. It was noted earlier that we have three methods for selecting tasks and frequency of cores: LEF, LPF, and LUF. In our simulations, we choose the best scheme to achieve the low power and energy consumption. The charts show the average increase in the power consumption is about 25% as the core number and utilization increase, and the average increase in the energy consumption of task replication is about 22% based on the number of cores and utilizations. To have a fair comparison between standby sparing and task replication methods, we suppose a dual core system and we consider the same utilization for all methods. The system is considered to be a dual core system because we consider the standby sparing method as a method for a heterogeneous system that require at least two cores to utilize the low power and high performance characteristics simultaneously. For this reason, we also consider the dual core for the task replication system so that we can run tasks and replicas at the same time. We evaluated the methods under two different utilization levels. The effect of heterogeneity on both power consumption and execution time can be seen in the charts. The left chart shows that generally the standby sparing methods, especially those that consider the overlap between primary and backup tasks, have a better execution time than task replication. It has also been shown that using standby sparing methods can reduce average power by 29% on average compared to the task replication methods. And the right chart shows increasing the number of replicas in some cases it can act similarly or better than standby sparing methods, especially when the frequency scaling is not allowed. So our estimates show that the standby sparing method could perform energy saving on average 13% better than the task replication method. In conclusion, low power consumption and high reliability are two main objectives in designing embedded systems, especially hard real-time embedded systems. We compared different fault-tolerant techniques used for reducing power consumption of embedded system. Our evaluations showed that if the reliability target is dedicated, so standby sparing can achieve low power and energy consumption. But if we want to increase reliability, we should note that the task replication will increase power and energy, and the frequency level of course plays a significant role in management of power and energy. Here you can see the references that I used for this presentation. Finally, I would like to take this opportunity to thank the Artist Organizing Committee and all reviewers who had valuable comments for our paper, and thanks those who took the time to listen to my presentation. If there is any question, I would be happy to be able to answer it. Thank you very much.